Hello again. In the previous lesson, we completed our work with polynomial functions. Now we're moving into rational functions. So in this lesson, we'll identify things like domain restrictions, vertical asymptotes, poles, intersects, some of the things that you've already discussed. So let's begin with example number one. You can review those quick rules um, on your own time. We're going to go through those. So we have f of x equals x plus 2 divided by x minus 3, and then we're going to state all of these. So the first thing we want to do is find the domain. Remember, the domain is when the denominator cannot equal to 0. So we have x minus 3. We know that it cannot equal to 0. Add 3 to both sides. We have x not be equal to 3. Okay, so that's one domain restriction. So the domain is all real numbers with the exception of 3. Okay, so we would write that as negative infinity, comma 3, union 3, comma positive infinity. Okay, since x is equal to 3, makes the denominator 0 and nothing cancels, x equals 3 is a vertical asymptote. Now, let's find the horizontal asymptote. The numerator and denominator both have the numerator and the denominator both have a degree of 1. So when the degrees are equal, the horizontal asymptote is the ratio of the leading coefficient. So the top coefficient is 1. The leading bottom coefficient is also 1. So the horizontal asymptote is y equals 1. Now we need to find the x-intercept. The x-intercept occurs when the numerator equals 0. So we have x plus 2 equals 0, which is going to give us x equals negative 2. Okay. So the x-intercept is negative 2, 0. Now we need to find the y-intercept by substituting x is equal to 0. Okay, so the y-intercept is 0 comma negative 3. Right? Example number 2. Compare horizontal asymptotes. So find the horizontal asymptotes for each one. Have A, B, C. Let's deal with A first. So we need to compare the degrees. So we have a degree of 1 and a degree of 1. Um, the numerator, excuse me, actually the numerator has a degree of 2, and the denominator also has a degree of 2. So the degrees are equal. So the horizontal asymptote is the ratio of leading coefficients. So if we have the top and the bottom is 2, and the leading coefficients are 3 and 1, the horizontal asymptote is y is equal to 3. This is for part A. For part B, the numerator has a, excuse me, the denominator has a degree of 2 and the numerator has a degree of 1, right? Okay, so a degree of 1 and then also a degree of 2. So the denominator degree is larger. When the denominator degree is larger, the horizontal asymptote is y is equal to 0. Okay, so again, um, that's a top degree of 1 and a bottom degree of 2. Okay, all right. And part C, the numerator has a degree of 3 right here, and then the denominator has a degree of 2. So the numerator is larger. When the numerator is larger, there is no horizontal asymptote. Okay. Okay. Make sure you review this. Now, in this case, the graph may have another type of asymptote later, but it does not have a horizontal asymptote. Okay. Pause and try the problem at the bottom. So we have this expression here, 2x squared minus 3 divided by x squared plus 4x plus 3. So the denominator is x squared plus 4x plus 3. We need to factor that. So remember, we need to think of a number that multiplies to give us 3 and that adds up to give us this plus 3 plus 1. Okay. Now we need to also, according to the zero sum theorem, we need to set these equal to 0. When we set this equal to 0, x plus 3 minus 3 is going to give us x equal negative 3, which that is an impossibility because remember, we can't have a denominator that is equal to this. And we also have x plus 1, 0, subtract 1. X cannot equal negative 1 either. Okay. Okay. So since that's the case, the domain, the interval, the domain is going to be negative infinity, negative 3, union negative 3, negative 1, union negative 1 tends to positive. Okay. Again, since nothing cancels with the numerator, both restricted values create vertical asymptote. So in other words, I'm going to abbreviate this as VA. You'll have a vertical asymptote of x is negative 3, x is to negative 1. Right? Now find the horizontal asymptotes. So again, this has a power of 2, this has a power of 2. When the degrees are equal, when the degrees are equal, we use the ratio of the leading coefficients. We have a coefficient of 2 and a coefficient of 1, which means that the horizontal asymptote is y is equal to 2. Let's continue. Example number 3. Here we have r as a function of x. We're going to simplify the function, state the domain, and identify the whole. So first of all, we need to start by factoring the numerator. The numerator is x squared minus 9. This is the difference of two squares, x minus 3 and x plus 3. Right? So now we have r parentheses x equals x minus 3 x plus 3 divided by x minus 3. Now we can simplify by canceling the common denominator, right? These are common denominators. When we simplify that, we'll end up with x plus 3. So essentially, r of x equals x plus 3. But the original denominator obviously was this expression here, x minus 3. So that means that x is equal to 3 is still excluded from the domain. Okay, never forget that. So the original was x minus 3. Add 3 to both sides. We have x positive 3. So again, that's a domain restriction. So now that tells us that the domain is going to be of infinity 3 union 3 positive infinity. Okay? Because the factor canceled, x equals 3 creates a hole, not a vertical asymptote. So to find the y value of the hole, we would substitute 3 into the simplified expression. So we would say, using this expression here, okay? What does that mean? The hole exists at 3, 6. So the graph looks like the line y is equal to x plus 3, but with a hole at 3, 6. Okay. So if we were to graph it again, this is essentially saying y is equal to x plus 3. If we were to graph this, 1 plus 3, so on and so forth, it would look like it would have a hole at that point there. Okay. Example number 4. So for q of x, we're going to find these things. Let's start with the domain. Okay. We're just going to go in order. So the denominator cannot be equal to 0, so that's x minus 2. So we need to write x minus 2 cannot be equal to 2. X cannot be positive 2. So that's one of our domain restrictions. So that means the domain is going to be negative infinity 2 union 2 positive infinity. And since nothing cancels, x is equal to 2 is a vertical asymptote. Okay, the vertical asymptote is x equals 2. And the numerator and the denominator both have a degree of 1. So the leading coefficients are both 1 for this one and 1 for that one. So the horizontal asymptote is y equals 1. Now we need to find the x-intercept. Okay, to find the x-intercept, we set the numerator equal to 0. So x plus 1, 0. That's going to give us x equals -1. Gives us -1, 0. That's the y-intercept, or excuse me, x-intercept. Then q equal to 0. We have 0 plus 1. That's divided by 0 minus 2. It's going to be -1/2. So that tells us that y would be 1/2. Okay, and that's our y-intercept. Now, choose, it says 2 test points. Okay, so we're going to use 1 point on each side of the vertical asymptote. Let's let x equal 0. Or excuse me, x equals 1. Let x equal. Okay. If we let x equal 1, we're going to end up with, compute this, 1, 1 plus 1, minus 1, we're going to end up with -2. So the point would be 1. And then let's let x equal 3. So we have q3, so 3 plus 1, then minus 2, that would be 4. So the point would be 3, 4. So the test points be would be 1, -2, and 4. Okay. All right, so a common mistake, a student cancels x minus 4 and says x equals 4 is allowed. Explain why x equals 4 is still excluded from the original domain. So the mistake is forgetting that the original denominator. If x minus 4 is the original denominator, then x equals 4 made the original denominator equal 0. Even if the factor cancels later, the original function was never defined at x equals 4. So if the original denominator, I'm going to say the original denominator contains x minus 4, then x minus 4 cannot be equal to 0. Right? Again, canceling creates a hole. So it does not make the restricted x value allowed. So a cancel factor tends to a hole. An uncanceled denominator factor, you have a vertical asymptote. So cancel factor leads to a hole. Uncanceled denominator factor leads to a vertical asymptote. Okay, let's review. So rational functions equal the quotient of polynomials. You have domains that exclude denominator zeros. Uncanceled denominator zeros create vertical asymptotes. Cancel factors create holes. Horizontal asymptotes come from comparing values. So always start with the denominator of these rational expressions, then decide whether restricted values create holes or vertical asymptotes. All right, again, thank you for watching.